Good day. Let's consider what happens when you apply a force. Let's say this is a force in the x-axis, and this creates a displacement in the x-axis. There is no friction, right? And then what we know is that the weight and the normal here are perpendicular to the displacement. So the work done by this force, which is, by the way, external, I'm going to define the system as just this block. So the force is external. So this force is going to do work, which we know is force dot the displacement. But of course, this will be F delta X cosine of the angle, but the angle between the horizontal force and the horizontal displacement is 0. So this will give me 1. So the work is simply the force times the displacement. Because there is no friction and no other force in the x-axis, we know there must be an acceleration here. If we were to use the old equations of dynamics, right, we will say that because of this force, there will be an acceleration, and the net force is just simply Fx. So there is an acceleration. So that means the velocity initial and the velocity final will not be the same. And we know that the initial velocity and the velocity final are related through kinematics, through this equation. So the acceleration is velocity initial, velocity final, and 2 over 2 delta x. All of this is known to us thanks to our studies in dynamics and kinematics. But what about if we do this through work? We know that force is mass times acceleration, delta x, so the work will be mass, acceleration, delta x. But the acceleration is this, so v final square minus v initial square, 2 delta x, and then times delta x. This cancels the delta x, and what we find is that if I distribute the mass, we get 1/2 mass velocity final square, 1/2 mass velocity initial squared. So we get this little equation here that tells us that if there is work, which I'm going to signal that is external because the force was external to the system. If there is work, then this quantity changes. We know there is acceleration, the velocity is going to change. That we knew before. But now through this new equation, we understand that work changes something. I had told you before that work was like an interact transfer. And the currency is what we call energy. So doing external work on the system is going to change this. And this quantity we define this new quantity 1/2 mv squared as the kinetic energy of the system. This is energy that happens because there is speed, right? So we have the work external is equal to the change, is kinetic final minus kinetic initial, or the change in kinetic energy. So this is one way in which work can affect a system by changing its kinetic energy. Notice that if the work is positive, like in this case, where the force and the displacement are parallel, then the work is positive and the kinetic energy increases. If you have a negative work, like for instance, if the object is moving to the right but the force is going to the left, of course this will decelerate the system. Well, this will be negative work, and that will create a negative change in the kinetic energy. If the work is 0, then the kinetic energy doesn't change. This equation is so important that it even receives its fancy name. It's called the Work-Kinetic kinetic energy theorem. And is going to be very useful for us this semester. Notice that this is capital K, is not the spring constant, is another K and means kinetic energy. A few points that I want to mention right now is that the work, the kinetic energy is related to speed, not to velocity. So for instance, if something is in circular motion, right? So here there is a certain velocity, here is a certain velocity, here is a certain velocity, right? But if it's the same speed, then the kinetic energy is the same. And that means this work, the work done by the tension or whatever it is making this thing be in orbit, the centripetal force, is doing no work, right? So same speed means same kinetic energy, so the change in kinetic energy is zero, and so is the work done by any external force on this thing, right? Another aspect is that this theorem is not a general expression. It's a specific case of a more general expression that we will discuss in the next chapter. If we put numbers to the explanation I just showed you before, here we get the example, this example, in which what we do is understand that the work done by the normal and the weight are zero, that the work done by these force on the system is going to change the kinetic energy. So we know that the block is 6, the force is 12, and the displacement is 3. So if they want the speed after it has moved, right, it started from rest. So the work, which is force delta x cosine of 0, is kinetic final minus kinetic initial, but there was no kinetic initial because it started from rest. So the force was 60. Well, let's keep it like this, symbolic until the end. So 1/2 mv final square, and if you want the final velocity, then this is 2 force delta x over the mass, and all we have to do is plug the numbers. 12 newtons, 3 meters, 6 kilograms. I'm keeping everything in meters, kilograms, seconds. And when I do all these numbers, we get 3.5 meters per second. So this is just a little example. We're going to do more problems in class.